In problem number 8, we're given the cost function, c of x, which expresses the cost of manufacturing x units of a product. And we are asked to find the level of production x that will minimize a of x, where a of x is the average cost per unit. The average cost per unit can be calculated by taking the total cost of manufacturing x units and dividing it by the number of units x. Let's plug in the function, the cost function that's given to us for x squared plus 120x e to the power negative 3x, and divide by x to calculate the average cost per unit. And also let's go ahead and simplify this. So I'm going to split this fraction into two fractions, 4x squared divided by x plus 120 x e to the power negative 3x divided by x. There are some cancellations that we can make here. For the first fraction, 4x squared divided by x, the square cancels out with the x in the denominator. For the second term, a factor of x and in the numerator and denominator cancel out. So with these simplifications, the formula for the average cost per unit function is 4x plus 120 e to the power negative 3x. And what the problem is asking us to do, it's asking us to find the value of x that will produce the smallest possible value of this function. What value of x should we use in order to obtain the smallest possible value for this function? In order to determine this value of x, we differentiate our function. We calculate the derivative of this function, and we will set this derivative equal to 0 because the minimum or a maximum of a function is always reached either at a critical point, a point where the derivative is equal to 0, or at the endpoints of the interval on which we're looking for the maximum or minimum value. In any case, when we're looking for the maximum or minimum value, investigating critical points is very important. So let's begin with that. Take the derivative of 4x plus 120 e to the power negative 3x. We differentiate term by term. The derivative of 4x is 4. The derivative of the second term, when we differentiate the second term, we need to use the chain rule. The reason that we need to use the chain rule is because the exponent here is negative 3x and not just x. And by the chain rule, this derivative will be 120. That's just a constant factor that we have in our function. Then we're going to have an e to the power negative 3x. This is because the derivative of e to the power x equals to the to itself, e to the power x. But here is where the chain rule comes in. We need to multiply all of that by the derivative of negative 3x. Okay, and so the derivative of negative 3x, of course, is 3. And altogether, we get 4 minus 3 times 120, 360, e to the power negative 3x. Let's go ahead and set this equal to 0. And then proceed to solve for x to find the critical points. Okay, so let's move our terms around a little bit. Basically what I want to do here is solve for the exponential term. 360 e to the power negative 3x equals 4. Now, let's go ahead and multiply both sides by e to the power 3x. The reason I would like to do that is because the exponent of the exponential term on the left-hand side is negative 3x. I would rather work with e to the power positive 3x, although it makes no big difference. Now, e to the power 3x times e to the power negative 3x, that is 1, and so those two cancel out. And then if we now divide both sides by 4, we'll be able to solve for e to the power 3x. It's going to be 360 divided by 4, and that's 90. Next, to solve this for x, this is an exponential equation. Let's rewrite the right-hand side, 90, as a power of e. The left-hand side as a power of e. If we can write the right-hand side as a power of e as well, then it will be easy to proceed with the solution. Now, 90 is e raised to the power natural logarithm of 90. This is the definition of the natural logarithm. And now our equation says e to the power 3x equals e to the power natural logarithm of 90. And therefore, since the two powers are the same, the bases of these powers are the same, the exponents must also be the same. 3x equals to natural log of 90. That's what we find. And now divide by 3 to find that x equals natural log of 90 over 3. Our function has only one critical point, but we don't know yet which one. Now, if you plug in x equals to 0 into our derivative, we will quickly see that that value is negative. So maybe I should do the full diagram, sign diagram for the derivative. I'm going to draw the number line. I'm going to find, mark on this number line the critical point that we found, natural log of 90 divided by 3. And then this is the only critical point that this function has. This critical point divides the number line into two segments. And I would like to determine what the signs of the derivative are on each of these segments. On the left-hand side of our critical point, we can select a test point, for example, 0. And if I substitute 0 into our derivative, which we calculated earlier, and I have a formula for it somewhere here. Yeah, right here. So if we plug in x equals to 0 in here, e to the power 0 is 1, and we're going to get that this value of the derivative at 0 is 4 minus 360. This is a negative answer. So the derivative of our function is negative to the left of the critical point. On the other hand, if we choose for x a large positive number, e raised to the power negative 3 times that large positive number is going to be really, really small, very close to 0. And therefore, the value of our derivative is going to be positive. You could actually, if you like, use a test point. So, for example, you could plug in 100, for example, or 1000 for x and see what the value is. But for instance, I'm gonna, let's say 100. This is definitely going to be a positive value. And so our derivative is going to be positive to the right of the critical point. And what does this tell us about the function itself and also this critical point. So to the left of the critical point, the function is decreasing. And then to the right of the critical point, the function is increasing. So the graph schematically looks like this. And so we see that the minimum value of this function is reached at this critical point. Okay. And so our answer is that the minimum average cost per unit is reached when the production level x equals to natural log of 90 divided by 3. And this can, of course, be calculated using a calculator.